Good morning, everybody. Thanks for coming to this talk. I'm very happy that so many people are interested in large infrastructure monitoring at CERN. So my name is Matthias Braeger, and I'm responsible for a technical infrastructure monitoring project at CERN. And so this is the agenda for the talk. I will mainly talk about in-memory data management and give an example of our project. But I want to show you also in a user points perspective how CERN is dealing with big data. Okay, before we dive into the topic, I would like to show you the different kind of data that we have at CERN and that we have to deal with. So first of all, there's of course this big chunk of physics data, which is more than 100 petabyte that we store already. But another big one is the metadata of the physics data, log data, of course, configuration data, and on the other hand, then the sensor data for technical installation. So you can divide this in two parties. So there's, on one side, there's data at rest, which has been stored somewhere. This is everything which is in black. And then you have what we call data in motion. So these are the sensor data which comes in from the different technical infrastructures and which you want also to analyze, but in real time, in memory. Just maybe some slides about CERN, because people are normally also interested in what we're doing. So we have been founded in 1954. It's already 60 years ago, and it's composed of the 21st member states. We have in total 3,300 staff and in 10,000 scientists that are working constantly at CERN. Our budget is 1 billion Swiss francs a year, and that's quite a lot, yeah? So you might think, what's the added value then for everybody of us? So as always with fundamental studies, you start your journey and you don't know what comes out, but to really make the LHC happen, there were many things which have been produced in the past. So, for instance, the World Wide Web was born at CERN. It was Tim Berners-Lee who did it. And we work also close together with the industry, for instance, with hospitals, because in the end we have a hadron collider. And this is now also used in the medicine. So there are around the world 40 hadron therapies center for treating cancer. And CERN is, for instance, also leading in grid technologies. So these are just some examples how things comes back to the industry from physics. So we are running the world's biggest machine called the Large Hadron Collider, or LHC, which sits 100 meters under the ground. And it has 4 big detectors, which is the Atlas, CMS, ALICE, and LHCb. And this is then where the collision takes place. And LHC, this is just the accelerator which transports the particles, normally protons, to the light of speed. So it's 27 kilometers in circumference, and you have superconducting magnets which are used to bend the data and so that they go really in circles. And the data run 11,000 times per second in this 27 kilometers ring. So we started operation of the LHC in 2010, and even if it doesn't mean much to you, even not for me really, we collide with 3.5 tera electron volt in each direction. So there are 2 beams, and when the collision takes place, it's basically with 7 tera-electron volt in total. So this has been then increased in 2012 to 4 + 4. Then there was a shutdown between 2013 and 2015. It was the first long-term shutdown, and there we upgraded the machine. And now since April we are back, and we can again do experiments, and we are now able to run with 6.5 tera-electron volt in each direction, which means also more data in the end. So these are just this. I show this as an example for one of the experiments. This is the biggest one, the Atlas. It's high as a 5-floor building, and there are 100 million channels inside. So meaning 100 million sensors who can send a signal. And this is where then the collision takes place in the middle. So I don't know if you see it in the picture in the middle. There's actually a guy standing in front of it, just to give you an imagination of the size. It's really huge. And it's under the surface, as I said. So when the data collide, we have raw data which are so that generate 1 petabyte per second. 1 petabyte per second, right? So this is an amount that cannot be handled, even not today. And what happens in first place, you have to reduce this amount of data to interesting events. You can think about an accelerator also as a 3D camera, and what you make are pictures. And each picture is 1.6 megabyte in size. So what we do is we have 3 levels of filtering. One is a hardware filter, which directly reduces a lot the amount of data, and because we can really easily filter out what is interesting and not. Mainly what is not interesting is events that are already known, because the physicists are searching for new events, like for instance the famous Higgs boson that has been found in 2012. So then there are 2 software layers to filter, and in the end you end up with a 320 megabyte per second. So this is something that you can handle, yeah. And what you can think of now, the software layer is basically already data management, so in-motion data treatment of physics data, right? So, but this is only one of the experiments, and this, what you see here, is a diagram of all the we have in total 9 accelerators at CERN, and they are all connected together. And I don't explain now the details, but just to give you an impression that we treat a lot of data from different experiments. So in total, we end up with 30 petabytes per year of physics data. Now the big question, and I would like that you raise your hand, who thinks that we use Hadoop to store all this data? So 1, I see 1, not so many. Okay, the question is, the result is no, it's not Hadoop, so I'm sorry. It's plain old tapes. And I give you the reason for that. Why tapes? But the good question is, or for those who are interested in Hadoop and think I will also talk about Hadoop, we store the metadata of the physics data into Hadoop cluster. So I will now explain you a bit more of that. So first of all, so we have this 30 petabytes per year, and it needs 100,000 processors to, first of all, collect this data, and then to write them down to tapes because there are peaks of 20 gigabytes per second. And this is a lot, and also not really maintainable to just store on disk. We would just run in the server center and always had to add more disks, if you like. And so we have 80 tape drives spread across to handle this. And in run 2 now, from this year on, we expect more than 50 petabytes per year to be stored. So we have, since 2013 already, 100 petabytes in these tape libraries, and they are stored in 55,000 tapes. And we have then a second layer where we store 13 petabytes on disk. So this is, if you like, the hot data, the ones that the experiment or the physicists then all over the world are interested in. So they can send a request to us, and then we get them back from tape on disk. And normally this is not instantly after the experiment has taken place, but maybe 2 months later, when the physicists are back in their research institutes, then they make a request and say, okay, I want now to get my data to work with it. So they can wait 5 minutes. Yeah, that's no problem. And later on, then it's fast because it's on disk. So there are 150 petabytes free tape storage waiting for run 2 already. And so why tape storage? So the cost of tape storage is a lot less than disk storage. And then think of the electricity consumption. A tape doesn't need any electricity, doesn't use any electricity if you don't need the data. So that's a big plus. And another thing is then they're very reliable tapes. So it's enough to keep one backup copy. When you're in a Hadoop storage, normally what you do is to keep at least 2 copies. So it's by the amount of data that we have, you would even need more to store it on disk reliably. So as I said already, the physicists, they have no requirements to keep everything ready within seconds. They can wait some minutes. All right, but I said the metadata of the physics data is in Hadoop. So in IT, we have relatively small teams which are responsible for a lot of different services that they have to provide to these 10,000 scientists at CERN. And what they have set up is an HBase service at CERN. So you can just ask for your HBase cluster to be initialized, and then you can use it. And there are currently, 3 bigger HBase clusters which have been set up. One, it's this Castor cluster with 10 servers. And so this is to keep the log data of, to explain, Castor is the tool that we use to store the data on tape. And to follow up if everything is correctly stored, we keep the logs into an HBase cluster for analytics. Then there's the Atlas cluster. This is from the experiments that I have showed you. And there we keep the index catalog. So basically, for all the experimental data that are stored on tape, you can browse them through this index catalog. And then there's a third one. This is for the monitoring cluster for the computer center at CERN. Right. So the first example with the tape storage event logs, you want to know things like on which tape is my file restored, is there a copy on disk, and so on. And then the administrators, they can quickly look it up and can then see exactly where has the physics data gone. It's for tracing. And the other example is then to know really, so this is more for physicists. I mean, they for them interesting is to then get some physical metadata of their experiments. For instance, you can think of the Atlas detector like an onion. It has many layers of detectors for different particles. And sometimes you want to know, okay, I'm just interested in this line somehow, all the basically triggers that have sent data then for this event. So you can do this kind of queries then against the H-based cluster. And what they do for this is they have a stomp broker. This is a message broker, if you like, which then where they send then this metadata via JSON, and this IE buffer that you see, this is just an event index buffer where they collect then events that belong together, and then they store them in bunches then to Hadoop. So this again examples then a bit what I told you already. Give me the reference to this event in that format for a given processing cycle. Right. Now that's just was from a user perspective, because I'm also not really involved in that, but I'm more involved in memory data grids and streaming analytics. So that are tools that we use then for the large infrastructure monitoring project that I'm responsible for. And there we deal with the sensor data of the technical installations. So this can come from different kind of installations like cryogenics, the access, computer center data, and so on, electricity. So what we see is, everybody sees that, I mean, is a big growth of data. And we collect more and more data in higher rates. And but first of all, big data means also a big cost factor. And it only makes sense to collect your data if you also do something with it and you analyze it afterwards. Otherwise, for your company, it's first of all cost, because you have to put the infrastructure in place to collect the data, to store the data. And to get a maximum return of investment, it requires good analytics tools in the end and well-defined target goals to harvest the precious insights of your data. So you have to keep that in mind. And then another aspect is the value of real-time. Latency matters a lot in the industry. So I've just saw a number, I wrote it down. It's that for Amazon, if the request takes 1 millisecond longer, it makes 1% in the sales that decreases. So the faster they are, the more they can sell, right? And so time is money. Then you have to meet uptime, service level agreements, and so for instance, in our case, we have a really demanding service. We have to be up 24/7, and we don't want to rely too much on databases, because they have also to be patched and maintained, and if they are off, our service has still to be available. So we try to push as much as possible in memory to meet our high demands. And what we see in the past is also a shift from data just stored on disk, on traditional relational database or NoSQL databases, then going into memory. And why that? Because RAM is 85,000 times faster than a disk, and still 2,000 times faster than a solid-state drive. So when you look on your data storage stack, you have on the top the process in memory, which is the fastest. I mean, there we talk about microseconds. Then you can keep this is your local off-heap memory. This is normally what doesn't belong to your application, but which you can put in RAM, where you can then, this can be also on another machine. So there it's around microseconds and milliseconds. And then on the top, on the bottom, then you have your relational databases, Hadoop or other data warehouse. So can we achieve high availability with RAM, or how is it working? It's that there are many different solutions, but what the vendors do is normally they replicate then the data on another node, and you can then set up how many backups you want to have on other nodes in your cluster of the data in RAM. And why is it happening now? Why are the companies using more and more this in-memory solutions? It's because there's a steep drop in price of RAM, and on the other hand, people want to have the data or the results faster than ever. So we get really used to it. I mean, when we do a Google search, I mean, it's instantly, yeah? We don't want to wait seconds anymore to get our results. It must be really fast. So what in-memory data grid or IMDG platforms provide is the scale of NoSQL. So when you are just considering about using something like MongoDB or Cassandra, you can do it also with in-memory technology. So maybe you should have a look on that. And they offer low latency databases, and they're very reliable and fault tolerant, and have also transactional guarantees. So basically you get fast big data within memory solutions. So here it is how it could look like. I mean, normally on the left, you see a traditional application, which is completely relying on the database. Everything is either in a NoSQL database or a traditional relational database. But then you can start putting small fractions or data sets into memory. And so to get faster response. And so what we found out is, oh, it works quite well, yeah? So why not putting more and more? So we get less and less dependent on the traditional databases, and we put even more into memory. And this you can also distribute then over different machines. And the solution on the market allow you to cluster. Right, so use cases for IMDGs are when to overcome legacy data bottlenecks and cache data, for instance, transient data. So just, I mean, when, for instance, you have some shopping, somebody does shopping in the web, I mean, this transient data you want normally to have in memory, and later on, when the transaction is done, then you put them on disk, I mean, for backup or whatever, but this is a very likely use case. So it's very often now the primary store for modern apps, and it's, as I said, NoSQL database in memory speed, and data service fabric for real-time data integration. So here are some in-memory data grid solution. I think this is like, it's a research that has been done this year from Forrester Wave. And you can see the big players are Oracle, Software AG, IBM. But there are also very interesting open source solution nowadays, which should be considered. Like, for instance, Hazelcast. And also from Software AG, Terracotta offers an open source solution beside their enterprise solution. Another thing which I would like to show you is how do you analyze data in motion? So you use data, you're streaming, basically doing streaming analytics, not from your data which are already on tape, but as they fly in. And this is not very often, I don't see it very often in the conferences nowadays, but there are technologies which are quite interesting, and they are used, for instance, in the banking sector, where you have to do decisions in a millisecond fraction to then buy or sell shares. And what banking's use normally is complex event processing. So what happens is you get your data streams in, and you can analyze them in real time, the same thing that you would do then with Spark on your Hadoop cluster. But in the end, you get then events out of the CP engine, which you could use, for instance, for filtering, and store just the filter data into a Hadoop storage, or to trigger actions, or alarmings, etc. I mean, it's up to you to define that. And all the data that is needed then, because it can also do queries over time windows, is then kept in memory. And they're quite performant. I mean, they can do easily up to 40,000 different events per second in one node. So there are many existing products for this. Unfortunately, there's no standard which has ever been defined. And but what is very interesting is Asper. That's an open source solution that is very robust, which comes also on top with an enterprise edition for clustering. And they provide an SQL-like query language, which is very understandable then from persons coming from the SQL, which are already SQL experts, let's say. And I just want to point here to a project called JEPC, which is from the University of Marburg, and they tried to make an attempt to standardize the event processing. So basically to put a middle tier, like you have it also for databases, that you're not relying in the end of one solution, but that you can easily then replace it by another one. Yeah? This you should do anyway, always, when to not be dependent on the end product. So there are many use cases in life. I already talked about banking sectors, but also like big companies, Google and Amazon, they need in-memory analytics and streaming analytics and in-memory databases. All right, I give you now a concrete example from CERN. Just check. Okay, I have 10 minutes. So we, in our project, we deal with data coming from various technical sites, so access control, network, hardware controls, electricity, safety systems, cooling, cryogenics. And I'm responsible for the technical infrastructure monitoring service, which is operational since 2005, and it's used to monitor and control these different technical infrastructures. And on top, we have then 40,000 different alarms which have been defined over the years. And so already because of that, we have to be up and running 24/7. So our challenge is not that we have a lot of users, we have a lot of data coming in, but our users are then the users in the different operation rooms. So and they are quite demanding. And since 2012, we are based on the C2MON platform, which is the CERN control and monitoring platform, which I will explain you in a few minutes. So as this is a bit the architecture of TIM, so we have a 3-tier architecture. On the bottom, we have a data acquisition and filtering tier. This is where we connect to the different technical equipments, and each of them have normally different protocols, as always. I mean, when you have a large fabric, they are not really big. I mean, everybody has a bit his protocol. So we try to unify that and then send the data to the server in a uniformed way, which is the value of the sensor, the timestamp, and its quality. But already here we do a lot of filtering. Out of this 400 million raw data values, we get then 2 million updates only that we send to the server, and the rest are redundant values or too precise measurements which are not interesting for the end user. And like that, we reduce the amount a lot, and this is then something that you can handle, that you can store also then in your, then to make trends and so on. So we have around 90,000 data sensors, 40,000 alarms, and around 1,300 rules which are based on these sensors to make bigger sense. And then on the top we have different client applications which are used by the operators. The main one that is used is the TeamViewer, which is basically allows the operators to make dashboards, and they are animated then by the data in real time, which are coming up. So, and this is, as you can see, the TIM server is based on this C2MON platform, which stands for CERN Control and Monitoring Platform. That's something that has been developed out of the former TIM server and now is used by 2 big projects at CERN, because we didn't want to reinvent every time the wheel when somebody had the need for a new monitoring system. And that unfortunately happens over and over, happened over and over again at CERN, that because we are so big, you don't know what your left hand is doing. And then we found out, oh, look, they just did the same what we did. Yeah, oh my God, it happened again. So what we have put together is then the core requirements of every monitoring system, which is data acquisition, then reliably storing the data, and sending the data out to the client here. So it's modular and scalable at all layers, so horizontally scalable on the server and DAC layer. And it's based on in-memory solution, and everything is written in Java. And the data is between the different tiers is sent via Java Messaging Service, JMS, and here we use an open source software called ActiveMQ. So this is a bit how it looks like. So as I said, you can cluster the C2MON server, and we have a distributed shared memory in memory, where we keep then the latest sensor values that have been sent from the DAC, and I'm good. And the rule logic is there, and all the configuration is there. Like that, we are completely independent from the database at runtime. So whenever we restart one of the data acquisition modules, and we have many of them, and they get their configuration from the main server, which has the full configuration in memory. So it's a central store for the entire configuration of the system. And the historical values are unfortunately today still kept in an Oracle database, but we are working hard on it to get rid of that and to use an open source a time series database. And I will show you what we have in mind for that. This is just, if you unbox the server, you can see that we have a server core, and on top we have then modules that we can write for the different use cases. So the Diamond project is using slightly different modules on the top than we do, for instance. But the core is then the same. And so there's something called JCache, which is a standard for in-memory caches. And now the big vendors, they implement against that interface, which makes it easy for the end user to plug and replace just the different technologies, and normally everything should work as before. So open source time series database, this is quite interesting for everything which has a timestamp and where you want to record your data over the time to keep the history. And so the four big ones, I mean, there are also other solutions, but the big ones are OpenTSDB, which uses HBase as a storage model. There's KairosDB, which is on top of Cassandra. But a new interesting one, unfortunately in beta still, it's version, I think, 0.96, is InfluxDB. It's the first native time series database, and it comes with an SQL-like language, which makes it really easy then later on to get out your data or make averages of your data. So it's also then later on a replacement for round-robin databases. But I think the most complete currently is probably Elasticsearch, which is also open source and built on top of Apache Lucene. And what is interesting about Elasticsearch, it comes with its own graphical tool called Kibana. And I guess many of you have heard already about that. And it gives you a very nice graphical output. And you can customize your dashboards. And what we use that already at CERN to put all our log data from all the different applications that we have in one central place in Elasticsearch, and then we have this Kibana tool, which allows you then to make queries on your log data. And Elasticsearch is there really fantastic because you don't need to do much. I mean, it does automatically generate indexes for you and speeds up, and it uses also in-memory technology just to speed up then your queries. Another one is for InfluxDB, and the other solution that I've shown is Grafana. Grafana is built on Kibana, but it's then for the other solutions, because Kibana is for Elasticsearch only, and Grafana is for supports other time series databases. And as you can see, it's also very complete and gives you a very nice output in few seconds. Right, so there's, what I show here is just a scenario how we have set up currently at CERN our monitoring service. So what you can see here again are the different DAC processes, which send then the data to a JMS cluster. And we have currently just 2 brokers in, but this is just for keep the high availability, so they're on different switches. And if one of them, for instance, if there's a network problem on one side or the machine is down, the other one can directly take over. And then we have 2 C2MON servers running, which share their memory in Terracotta. So we use the open source version of Terracotta, and that comes even with a standby, so a mirror, to have this high availability also on your in-memory store. And if you like, the C2MON server are like that, stateless in a sense. So they can pick up the data as they come from the JMS queues. And so it's a fully load balanced solution. And what we can now do is, if we have a patch and we know it's compatible with the current model that we have in Terracotta, then we can just do rolling updates. We stop one server, we patch it, start it up, then the other one, and like that, we achieve our 99.97% of uptime per year. This is what we had last year. And then for the client tier, we do the same. We have, again, JMS brokers, and the clients, they, if you like, they don't connect directly to the servers, but only to the brokers. So it's an anonymous communication. And this is quite nice because like that, even if one server is down, they don't see it. We can then also move the servers to another machine, and they don't care because it's all shielded by the JMS brokers. A little riddle, a quick one in the end. Do you know what GQ means? So normally there's another acronym called GIGO. It's garbage in, garbage out. But what we try to do with C2MON is garbage in, quality out through the filtering on the data acquisition layer to reduce already your data before you store it into your time series database or into whatever you like. Yeah? So we think that raw data filtering is very important already. You should reduce the data at the bottom and not going through the whole system and then only when you store it, or even to store everything. Yeah. This is just to show again that you could, if you have higher requirements and you have really many data, so for future scenarios at CERN, we could then scale out. We could add many more C2MON servers, and we could then, with the enterprise version of Terracotta, then also scale out the in-memory cache. So at the moment, we are not in this scenario, but we are prepared for it. So on the roadmap is we want to offer C2MON to the open source community. And I'm here the next 2 days also to get in contact with you and to see whether you have maybe an interest in your company for C2MON. And please check our website. Currently, you cannot download it. We are, at the moment, still sorting out a bit the licensing issues, but it's coming soon. And we keep on actively maintaining the product with adding complex event processing, and we will migrate then to the time series databases. Right. A last thing, just because it's something that now the marketing guys use always over and over again, is IoT, Internet of Things. Or shall we rather talk about Intranet of Things? Because creating a smarter world happens first in the intranet. And the challenge is then, for us at least, integrating heterogeneous systems and protocols. And this is what C2MON is great in, because you have then one platform where you unify, and once you have complex event processing in, you can make really complex rules to trigger commands to send back to your equipment. So you can influence at runtime your production system. And so there are many IoT solutions available, but they are often closed products, and they are not compatible to each other. So C2MON could be an answer to your problems. So, and what is then Internet of Things? I mean, the problem is here, of course, security, but what we have seen is for the industry, for instance, one good example would be if you have a product and many fabrics are using it, interesting for them is then to gather statistics and to analyze these statistics from a variety of installations, and this could then influence the product cycle and to make the next version of your hardware better by analyzing the problems which occurred. So this is very essential, and this is how I see Internet of Things, maybe a use case for the future. Okay, so takeaways, data and high availability services are more important than ever before for all modern organizations. and deriving values from collected data is the key to success. In-memory platforms are essential for high value and high velocity data storage and processing. Here, just some credits from talks from other people which influenced my talk, and also a full reference list of the pictures and the data I got from. I want to say muchas gracias por su atención, and thank you very much.
So before we go into the break, is there any questions for Matthias? No. Thank you ever so much again, Matthias.
Thanks.